So let's talk about LZ77 compression. LZ77 compression. Anybody know what the 77 refers to?
Page number wrong?
No. Good guess. Anybody want to take another stab?
Oh, we are on page 77, actually.
You're kidding.
Yeah, because we finished reading it 76, I think. So we're doing this.
That would be funny if LZ77 compression was on page 77, but it's not, right?
If it was.
It's like one page off? That's pretty funny. No, it's for 1977. It was when this particular compression technique was developed. All right? So it was another algorithm using dictionary coding published in 1977. And what this, the way this kind of differs from what we did with the Huffman tree, with Huffman coding, is that LZ77 looks for repetitions, right? It looks for repeating patterns in the data. And so, for example, if you have the word hello, maybe it's compressing a text file that's got the word hello in it. And so the first time it will encode hello to be whatever bits hello is supposed to represent. But when it encounters hello a second time, maybe as you go on down the file, 60 characters later, you encounter hello again. And so the basic way that LZ77 works is it says, okay, I'm not going to encode hello again. I'm just going to say, go back 60 characters and repeat the 5 characters that were there. Okay? So it records that in the file. Go back 60 and repeat 5. So it looks for, I'm dumbing it down, right? But that's in essence the way that it works. And so you can see for like common words that are repeating throughout, then this could definitely save you some space. You only have to encode that word once, and then you just have to have an easy way to tell it, go back this many characters and repeat this many. All right? So that's the basic way that LZ compression works. It is, I looked at the wrong page, and I was like, what? It's not lossy. It's another form of lossless compression, right? So it works well for text. But it works well for anything that's got a repeating pattern in it. All right? So that means it would work well for images as well. If you could find patterns in that image, and you could kind of point back and say, just repeat these patterns here, then you wouldn't have to encode each individual pixel, right? So that's a way that LZ77 could losslessly compress an image file. They use an example in the book, like for example in the book there's about 20,000 characters for about 15 pages of text in the book, and it would take up 20,000 bytes or about 19.5 kilobytes. Actually I thought he was talking about compressing the text. Actually he's comparing the text in the book to an image. So 20,000 characters in the book, if we digitally encoded that, it would take up about 19.5 kilobytes. But if you had an 8-bit RGB color 400 by 400 pixel image, which is pretty tiny, and if it's 8 bits, if it's RGB 8 bits, how many total bits is it per pixel? It's RGB color mode, and it's 8 bits, 8-bit RGB. So for one pixel, how many bits? Yes. Who?
2.
Nope. Nope.
24.
Who said that? Yes. You see why 80?
Yep, I
right? So it's 8-bit RGB, and so that means for each color, we're going to use 8 bits of data, right? And so for a total of 24 bits per pixel, right? That's a lot of data for a single pixel. And so if you've got a 400 by 400 pixel image, then you're talking, what is that? Is that 16,000? Is that right? 6 or 100? That's 160,000, right? It'd be 16 with 4 zeros after it. So let's see. We had Aiden, and we had. I know your name, dude, but I'm getting you confused with Preston. Dude, I don't know your name.
Levi.
Levi, that's it. Okay.
Look at the shoes he wears.
What's that?
The shoes are Levi's.
Oh, really? Is that always the case? Do you always have Levi's on here?
Yes, usually.
Usually, okay. All right, I'll have to try to remember that.
Just like next time you try like Mercedes.
Look at the shoes. All right, I got it. All right, so images get big really fast, right? Is the point. And so looking for repeating patterns, repeating colors, and things like that, that you can say, oh, we've got a string of this many colors, right? 18 pixels that are all this color blue. Let's just repeat all of those. Then it can be an easy way to compress that data, and a lossless way to do that. Unlike JPEG compression, which we saw when we did our JPEG examples, and we took the quality way down, was it lossless? No, right? If some serious pixelation. Some of you you took it way down, which is what I wanted you to do, and you saw like major pixelation when you took the quality level way down. All right. So let's look at digitizing images and kind of using a technique that goes along with this that looks for these repeating patterns. This is digitizing images. And so he's got this example in the book, and he does it wrong. So I'm going to try to straighten it out, and hopefully I won't make a mistake. But he just, with the way that he drew the image, he didn't do it quite right with look. So here's my, let's see, I'm going to do a grid that is 6 pixels wide. So 1, 2, 3, 4, 5, 6, and we're going to go 1, 2, 3, 4, and 5. Alright, so what this grid is supposed to represent is my computer screen, right? That's full of pixels, right? Which are just dots on the screen. It's a grid on the screen. And this particular image is 6 pixels wide. Right? So this is 6 pixels wide by 5 pixels high. And we're going to color in, this is just a black and white image. And so we're going to color in some of these squares here. Which is probably a bad idea because I'm using all of my marker. You can look at this in the book if you don't want to draw it yourself. But anyway, that's how it looks. So it's an image, a black and white image for the word high. All right, you guys see that? Can you see the high in there? You see it, Isaiah? You know, okay, all right, just making sure. I was hoping you weren't going to force me to use more of my black marker, all right? All right, so we've got the word high represented in black and white. And so if we think about this particular image here, if we let 0 represent black and 1 represent white, then in order to represent this image as a binary string, we could first use 8 bits to represent the width. And so we've got 0, 0, 0, 0, 0, 1, 1, 0. That's our width. And then we've got 0, 0, 0, 0, 0, 1, 0, 1. That's our height. And you guys should have been able to tell me that if I was using 8 bits, that would have been the width and the height, because you guys know how to count in binary now, right? And so you would have said, if we were trying to get 5 as my height, it would have been, this is 0, this is 1, this is, actually, if you're starting from 1, let's see where you're starting from. I'm not sure where you're starting from.
So he made 1, 0, 1. So 1, 2, 3, 4, 5. Yeah, he started with 0. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, and then 6 is 1, 1, 0. Right? So that's what, and it's just padded with zeros in the front because the width and the height are specified as 8-bit pieces of information. All right, so we have to store the width and the height of the image, and then we store the actual pixels that represent the image itself. And so if zeros represent black and 1 represents white, then we could draw it out like this: 0, 1, 0, 1, 0, 1. So I'm just going across here. Black, white, black, white, black, white, black, white. So 0, 1, 0, 1, 0, 1, 0, 1. I'm going to group it together in groups of 8 so we can keep track of it. So that gets us to, we just finished this one. So we have 0, 1, 0, 1, 1, 1, no, I'm sorry, 0, 1, 0, 1, 0, 0, 0, 1. So 0, 1, 0, 1, 0, 0, 0, 1, right? Say 0, 1, 0, 1, 0, 1, 0, 0, 0, 1. Yep. Then we go 1, 0, 1, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0, 1, 0. And then finally, we go 1, 0, 1, 0, 1, wait a minute, where were we? Lost my place. That's 8. Then it's here, so that gets us, that's that one. And then 1, 2, gets us all the way to here. And then we go 1, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0. And we add 2 more zeros on at the end because so that we'll have an even number where you have 8 bits for each of those guys. All right, so there's a way that I might represent that image digitally, right? If it's black and white, and zeros represent black and 1s represent white, right? Well, when we talk about LZ77 compression and the idea that you're looking for patterns that are repeating, when we look at this image, we can notice that at the start here, we've got black, white, black, white, black, white, black, white, black, white, black, white, right? We've got 6 black whites. You guys see that? 6 black whites. And then we have 2 blacks, 2 BBs. And then from there we go black, white. So 1, 2, 3, 4, 5, 6, 7, 8. So then we've got 8 more black whites. You guys see that? If we group it in groups of 2, yes?
So all of the ones that you put up there start on a black, but the second 2 sets of 8 start with 1 and not 0. I think you made a mistake there.
Let's see. Oh yeah, you're right. 0, 1, 0, 1. 0, 0, 0, 1. Yeah, this should have been reversed, right? All right, so let's do that. This should have been, goes all the way to the end. 0, 1, 0, 1, 0, 1, 0, 1, and then 0, 1, 0, 1, 0, 1, 0, 0. Is that it?
Yes.
Yep. All right. Because you're in the class, I'll write your name on the board since you corrected me, but you're grounded for the rest of the week. Thank you. Does that make sense, everybody? Sorry about that. So that's the way it would be if we just took the zeros and the ones and applied them that way. But if we looked at the repeating patterns, we could do something like this. Where we notice that, let's say we use 6 bits per run of pixels, 4 bits for the length of the run, and 2 bits to represent the pattern, okay? So let's say we had 0, 1, 1, 0. That's the number, let me put it here, sorry. 0, 1, 1, 0. That represents the number of times, right? We had this with zeros here so that we can see which one applies to each one. This would be 7, 0, 1, 1, 1, and then 8 would be 1, 0, 0, 0. So we use 4 bits to represent how many we've got, and then we use 2 bits to represent the pattern. In this case, it's black and white, so black is represented by 0, and white is represented by 1. When we've got 2 black blacks, 2 is represented by 0, 0, 1, 0, 0, 0, 1, 0, and black black would be 0, 0. And then 8 black whites, 8 is 1, 0, 0, 0, 1, 0, 0, 0, and then black whites are 0, 1. So by looking for the patterns and using that to our advantage with compression, then we took what was previously, we still going to have to record the width and the height information, but we basically took all of this data, which was 4 times 8, which is 32, and we compressed it down to only 18, right? So what we call this, when we're looking for patterns like that and using the patterns to viewing the patterns as runs in the code, this is called run length encoding. All right, so it's a method. It's a method of lossless compression where you consider redundancies or patterns. Another way to think about redundancies or patterns in the code. A method of lossless compression where you consider redundancies or patterns in the code. So you're looking for those patterns and you use those to your advantage to compress the file. We call that run length encoding. So unlike Huffman trees, right, which I had you do an example on the quiz, it's pretty easy for me to give you a word and say, hey, draw a Huffman tree for this. This is a little bit harder to do, so I'm not so interested in being able to draw an image and say, hey, tell me how I might compress that using 6 bits instead of 8 or something like that. I just want you to understand how this works, right? So I want you to get that you're looking for patterns. There's an algorithm that goes through and tries to identify those patterns, and then it bases the compression on the knowledge of the fact that there are repeating patterns in there. So we look at the data as runs in the code and where those runs repeat. So we call that run length encoding. Any questions about that? You know what? I just realized I'm missing the word runs. This should be as runs. Sorry, I was looking for that. And I'm like, where do I say that word? Runs in the code. There we go. Redundancies are patterns as runs in the code. Make sense? You guys get the idea, right? So don't stress over like studying this and making sure you can do this on a quiz or a test. I'm not going to give you that, right? But I do want you to understand how run length encoding works. Any questions about that? This is what, chapter 3? Is that where we're on now, guys? Yes?
Yes.
Yes. All right. And you guys just took which quiz? Was it quiz A or quiz B?
And
Quiz A. Okay. All right. So even though I don't expect you to do this, right? If I give you the image, I do expect you to be able to explain the process. So if I gave you a picture of an image and I was like, how might you do this? I don't want you to convert it to ones and these zeros, but you should be able to tell me how you're identifying the runs in the pattern, and you can compress it based on identifying those runs, those repeated patterns in the image. Okay. All right, so let's talk about, so that's digitizing images, and run length encoding is a way that you can compress those, but let's get into other ways to compress images. We talked previously about, there's a branch of psychology called psychophysics, right? Because I told you, I'll feel like I've accomplished something if one day you guys come back to me and go, hey, Mr. Walker, because of you, I am a psychophysician, right? I just think that would be a cool title, right?
Would it be psychophysician or psychophysicist?
Psychophysicist, I like that one too, either one.
I thought physician is like medical stuff.
Okay.
And like a physicist does like physics.
But it's a branch of psychology. So
So it would be.
it seems more like
Yeah.
maybe a psychologist.
I thought you said it was a branch of physics, not psych.
Did I? I don't know. It's a branch of psychology. I should have said branch of psychology.
Okay.
Yeah, sorry. So, but it's called psychophysics. That's the weird thing, right? So I was thinking psychophysician. That would be a cool title, you know, out on the road, James Walker, psychophysician. But anyway, I digress. Let's talk about compressing images, and what does that have to do with psychophysics? Well, in this branch of psychology, they've studied what the human eye is able to detect as far as colors are concerned, right? And so in doing these studies, in 2012, they released a study that said that the human eye can only perceive about 30 distinct shades. All right, so if you've got a color, and you've got all these different shades of those colors that you're able to represent on a computer screen, the eye can only detect about 30 distinct shades of gray, when they were studying gray specifically. All right, so if I've got an 8-bit image and a grayscale image, that's 2 to the 8, which is 256. And so I could represent 256 shades of gray. The computer is able to do that, but you can't tell it, right? If you can only see 30 shades of gray, then why would I use all 256 of these in my image? It doesn't make any sense. And so when you're compressing images, that's our topic, compressing images. If I, as in I, not I, yeah. If I can only detect, and I'd be curious, since I'm colorblind, I wonder if I can even detect 30, or could I only detect less? I don't know. If I can only detect 30 shades, then why use 256, right? And so some forms of compressing images, they say we shouldn't, right? We're just going to throw out all that extra data. I may take a picture out here and it may include all those various shades, but there's no need to have those in there because you can't detect it anyway. And so that is a form of what type of compression? If you're throwing data away that you can't get back. Yes? Lossy, right? So lossy compression says throw extra data away. We throw it away and we can't get it back, right? So there's no way to go back to the original image. That's why it's lossy. And what was the form of image compression that I had you guys use? Most of you use on the assignment. What format? JPEG, right? So JPEG is a lossy compression. And it kind of builds on some of the things that in this branch of psychology they've discovered, that the human eye can't detect it anyway, so why leave it in there? And so that's what I wanted you guys to see, you know, as you adjust the quality. I mean, our phones, some of our phones will take these amazing, as far as the quality of the image goes, the number of colors that are contained in them. I mean, it's amazing how accurate the representation is. But the reality is, our eye can't even perceive the detail that's contained within the image. And so a lot of times you can compress these images down, and you can't even tell the difference. I mean, several of you, when I was looking at your explanation when you adjusted the quality, you said, I can't tell. Some of you didn't change it enough, and you were like, it looked the same. All three looked the same to me. Yes?
It's part of the reason my highest quality and like middle quality looked very similar. Do you think it's because I took it as a 4K picture? Like the picture I used was 4K.
Right, yes, so
My-
super high quality, and so your
my
screen can't
display-
even really display.
Yeah, my
Right,
display is 1080p.
exactly. So yeah, that's part of it as well.
The point where I can.
Right, right. So yeah, the better quality of your image and the lower the quality of your display, the harder you were going to be able to. It was going to be for you to be able to tell a difference. So anyway, a lot of times you don't need that super high quality. You know, I work with video a lot, and the video files are humongous. In fact, I took the quality down on the phone for these that I was posting online because it was way better quality than I needed to post it to YouTube, right? And so they're half the size that they used to be on my phone. So this is something to think about when you're saving the files. You don't necessarily need that high quality image. Professionals might, for some reason, right? Because they're expecting, I'm not only going to view this on my 1080p display, but I'm going to stick it on a billboard or something. And so yeah, maybe you need that high quality, but most of the time we don't, so we can save some space. So let's talk about there's kind of 4 image formats that I want you guys to be aware of, and how they differ as far as compression goes. PNG, does anybody know what PNG stands for? Yes?
It's a portable network graphic.
Mm-hmm. That's exactly right. Supportable network graphics. And PNGs, for the most part, have replaced GIFs on web pages unless it's animated, because PNG doesn't support animation. You still have animated GIFs, but it is a lossless format based on LZ777 and Huffman Trees. And like I said, this is generally now preferred over GIFs unless need animation. All right, since we've mentioned GIFs, let's go ahead and list those as well. GIF is another popular image compression format. This stands for, who knows this one? Anybody else know this one? Yes?
Graphic interchange format.
Did you look at the book, Stephen?
Yeah.
An honest man, I like it. All right, graphic interchange format. And again, that's why I laugh on the inside every time somebody says GIF. You know, and we're not talking about peanut butter here, we're talking about digital images, right? It's not graphical interchange format, it's graphic interchange format. And that is also lossless. Uses a dictionary algorithm based on LZ78, next generation LZ77's successor. Like I said, they took a little while to go away. We still used GIFs for a while, but that was mainly due to browser support. Now most browsers support PNG, so PNGs are kind of more common for the web, unless it's a photograph, and then of course it's JPEGs. The last lossless format we want to talk about are bitmaps. The extension is BMPs, or BMP, I mean. and it is lossless, and it uses what we just learned about today, run length encoding. Uses run length encoding. And then finally, your assignment last time was using JPEGs, which stands for Joint Photographic Experts Group. So as the name signifies, this is typically used for photographs. It's lossy compression that breaks an image into 8 by 8 pixel blocks. And so it's a great compression technique for photographs. Not so good for other graphics. Usually PNG will give you a better file size, and PNG is lossless, whereas JPEG is not. So any questions about the different common graphic formats? No? So if I asked you what were a couple of the common formats we talked about in class, you could tell me those? And if I asked you what is a GIF, you would say. But if I told you to give me its abbreviated name, you would say. And I would say F. All right, compressing video. Let's talk about video compression. Got a lot of that floating around, right? Compressing video. It's kind of become a common way of life. Anybody watched any digital videos so far today? Show of hands. Anybody that's watched a digital video? Come on. All right, then there's something, right? Somebody, just about all of us, has consumed something. I think I can honestly say I haven't seen anything today, but it's that common, right? And so for compressing video, we talked about the necessity at the beginning of this chapter, how you've got like 4K video now, right? Which is huge, and there's just no way most of us there would be enough bandwidth to stream a full uncompressed 4K video into our homes, right? So you've got to have some way of compressing it, and there's two basic ways. Videos are just a series of what? It's just a series of pictures, right? Video is just a series of images, and it'll have a frame rate associated with it. And so if you've ever seen, like for video, 24 FPS or 30 FPS, what does that stand for? Frames per second, right? It's how many pictures are going by per second as you're watching that video. And so, since it's just images, then we can use some of the techniques we've already learned about for compressing images to compress video as well. And there's two main types that I want to talk about and just compare, make sure you understand the difference in the two. And that is, we have what we refer to as intra-frame. The spelling on this is subtle, so make sure you know the difference. Intra-frame compression and this simply runs the same compression algorithm on each frame. All right? So the same techniques that we've already learned about with compressing images
It just looks at each frame individually and says, compress this image, compress this image, compress this image. And that's how it compresses the whole video. One frame at a time, totally independent of one another. It just runs the compression algorithm on each frame. That's intra-frame compression. Now the other form is inter, not intra, but inter-frame compression. This technique compares frames to each other. Reusing redundant pixels from one frame to the next. So that's inter-frame versus intra-frame. Like I said, the name is subtle, the difference is subtle, so make sure that you catch the difference in the name there. Intra-frame says, I don't care what the other frames are doing, I'm just going to compress this individual frame. Inter-frame says, hey, I noticed from this frame to the next frame, there was like no movement except up here in this corner. So I'm just going to repeat the information that didn't change, and I'm only going to reuse those redundant pixels and only worry about compression with the data that's changed on the frame. Okay, does that make sense? One compares frames to frames, the other one looks at each of them independently. Any questions about that? Did anybody raise their hand? I wasn't looking. Sorry. Lancelot didn't raise his hand. All right, I just realized I spelled something wrong in my notes. Digital connections. All right, so again, there's a limited bit rate, right, going into our homes. My internet connection is 50 megabits. Yes, Braden's raised his hand.
Is like every sort of digital video kind of done the same way with one of those two? So that would be like movies and stuff, but then also things like even video games. Are video games done the same way?
Well, video games are different because you're not, like, if you're talking about streaming that stuff, like if you stream it now.
Well, I understand that like it's done a little differently because it's not all saved somewhere and having to be processed.
Right.
It's all processed on like at that time.
Right.
But would it still be using one of those two type of?
I don't think so because I know with like digital video games, a lot of that stuff, especially like with these very realistic games, there's like 3D models behind all that, so there's a bunch of math.
So you don't really have to actually compress anything. You just
Yeah, right, exactly. So it's just like drawing that stuff because you don't know what's going to happen next necessarily. Yes.
More if it's compiling, using more efficient compilers, DXC compilers, stuff like that.
Right. Okay.
More not as much compression, but compiling to be more efficient in the way that
So it can run faster.
Yeah.
Right? So compressing it down to like a native language that the computer understands versus the computer having to reinterpret the code every time it runs, right? So that's the way compilers work. You write it in a human language that you can understand and encode it, right? But then the compile part basically takes it and knocks it down to machine language so that because the machine doesn't care about verbs and nouns and stuff like that like we do, right? So yeah, good point. That's more what you need to think about when you think about video games. With video, like I said, we have 50 megabits per second is our internet connection. And just as an example, he says that 4K video uses nearly 200 million. So 50 megabits per second is 50 million bits per second. 4K video uses nearly 200 million bits per second. So, I mean, if it was in its raw format, I couldn't even stream 4K to my home, right, with 50 megabits per second. So, video compression is absolutely necessary if we're going to be able to transmit video across the wire, right? All right, any questions about these two primary forms of video compression? Everybody understand the difference between the two? Got it? All right. Cool. We have 14 minutes to talk about compressing audio. Let's talk about that. So there is a branch of a sub-branch that I mentioned of psychophysics. It has to do with audio. What's that called, Josh?
Psychoacoustics.
Psychoacoustics, exactly. So how would I say, what would my role be if I was practiced psychoacoustics, if I studied psychoacoustics?
Psychomusician.
Who's like the guy that checks your ears and does like audio tests and stuff on your ears? That would just be like an ear, nose, and throat doctor, right? Probably. I was thinking it's like some kind of auditory psycho. Anyway, so compressing audio. So two well-known uncompressed, two well-known uncompressed formats for digital audio are they have this extension, .aiff and .wav. Who uses .aiff?
That's math.
Right, it makes me hiss like a cat. Well, they just should have two buttons on their mouse. Come on, right? It's a no-brainer. Windows have two buttons, Macs don't. I guess you can get a Mac mouse with two buttons, right? So Windows is like kind of native uncompressed digital audio. I'm sorry, Wave is uncompressed digital audio. Windows format. Macs use AIFF. So those are two uncompressed formats. And when you convert, there's some, I think we've talked about this before. There's already some loss of data that takes place when you take a sound, a naturally occurring sound, and you convert that to digital audio, right? Because you're taking something that, I remember drawing this on the board. It's like you take your sine wave, right, that represents your audio, and you sample that to create a digital representation of it that kind of looks like a bunch of little steps, right? And depending on how many steps you have, it'll sound closer. And I'm not doing a very good job here, sorry. But you get the idea. It'll sound close or not so close to whatever the original sound wave was. And so this is what happens when you use a digital audio converter to bring sound into your computer, right? It converts it to this digital version of the wave. And so the sample rate which is measured in kilohertz or thousands. Kilohertz means thousands of samples per second, right? Because kilo means thousand and hertz is per second. So the sample rate is 8 hertz for phone calls. Just to get an idea of the sample rate, why some sound better than the others. 44.1 kilohertz for CDs. Not 8 hertz, I'm sorry, 8 kilohertz. Kilohertz for phone calls, 44.1 kilohertz for CDs and MP3s. 96 kilohertz for DVDs, and 192
kilohertz for Blu-rays. So just to give you a sense for how it changes with the better audio quality. The reality is that most humans can't distinguish differences if the sample rate is over 60 kilohertz. So if you go from your CD to your DVD, you may be able to tell a difference, but DVD to Blu-ray, you're probably not going to be able to distinguish a difference. As long as they sampled it over 60 kilohertz, it'll sound the same. So that's the sample rate. That's how often we're taking samples of that sound, right? So you've got that analog sound that's happening, that you're hearing as I'm talking to you, right? And then if you record my voice, what's happening right now on my phone is it's recording that and converting it to digital sound, is that it's taking a sample rate. And that's pretty amazing, right? It's not like so many per second, it's so many thousand per second. And it may be 8,000 a second versus 44.1 thousand a second. It's a lot of samples to try to accurately produce that natural, that analog wave that you're hearing as I speak. In addition to sample rate, there's also something that can affect the quality called the bit depth. And the bit depth refers to the number of bits used to sample the analog waves amplitude. What does the amplitude have to do with? Does anybody know? Volume? Volume, yeah. As the amplitude goes up and down, the sound will be louder or quieter. So like when we're looking at these different things here for CDs and DVDs, this is usually 16-bit. This is usually 16-bit. Oh wait, DVDs are 24-bit, sorry. 24-bit. So a little bit better with DVDs. I'm not sure what Blu-rays are. Maybe 24-bit also. But I want you to know this. So if you see the term, a lot of times we'll just combine these together and we'll use the term bit rate. And so bit rate is the bit depth and sample rate multiplied together. All right? So if we say so 44.1 kilohertz audio at 16 bits would be bit rate would equal 44 1000 times 16 equals 705,600 bits per second. So it's just the two multiplied together to get that bit rate.
Some common lossy compressions formats.
Two common lossy compression formats are MP3
And AAC. And like I said, both of those are lossy. All right.